Hello, this is Mr. Craig, and this is day 79, the review before the first acid and base quiz. And I am asking, or actually I'm making this video so that you are accustomed to some of the wording of some of the questions here, because a lot of you had, or some of you had some difficulty understanding what the questions were asking. And even though they weren't necessarily full acid and base type questions, some of these questions had some components or elements of things that we had talked about earlier in the year. And that was one thing that really caused a lot of you to get frustrated and confused about what is the question asking, because it's not purely acids and bases. The one thing that I want you to realize is that this course is building upon all the information that we have learned, and we're going to continue using that stuff. So I want you to get comfortable with these types of questions, because when it comes to the AP exam, or when we get to the AP exam, I want you to be familiar with the wording and not be so uncomfortable when you actually have to answer these questions. All right, so looking at number one. And what I did to number one is I actually added a couple other examples to it just to get you familiar with this. So yeah, all these examples on number one are not on your sheet of paper, but I would highly recommend that you pause the video and answer them before you listen to the example or the explanation. All right, question number one, it asks, what is the conjugate base for the bicarbonate ion? And again, this is not one of your polyatomics, so I don't want you getting all upset about the name bicarbonate. It's the name of the polyatomic. That's all you need to know. So the question is actually right here. What is the conjugate base for this? Now, you may or may not recognize that HCO3 with a -1 charge is amphoteric. This thing could act either as an acid or a base. So whenever you see a question like number one on the quiz or test or on the AP exam, they're going to give you an amphoteric substance. So you can't just look at it and go, oh, well, there's a hydrogen on the front of that. It's an acid. Well, yes, it is an acid sometimes, but it can also be a base, because when we look at that -1 charge, that means we've got room for one more hydrogen. So what I don't want you doing is automatically thinking that, yeah, okay, I remember that if it starts with an H, it's an acid. If it ends with an H, it's a base. True, most of the time. However, in questions like this, you're going to see amphoteric substances. Okay? So here's how you really should read this question. What is the conjugate base for this acid? Okay? So when you see a question like this, it's asking for the opposite of this thing. So it's asking for the conjugate base of what this thing actually is right here. So if the question's asking for the conjugate base, remember that it will always be the opposite of what it's asking. So if you really want to be smart about this, cancel out the word conjugate and just focus on base. So if you what is the base for this acid? Wow, that gets a lot easier. So you just have to now think about, okay, well, what do acids do? Well, in this case, the bicarbonate ion will give away a hydrogen. Now, you might be, and I did hear a few people today when we were going over the review in class, a few of you were really upset because I didn't give you anything that this was reacting with. Or you asked, is this reacting with water? And I kind of left it wide open, and I didn't really answer the question fully, but it's reacting with something. If you want to make it react with water, that's fine. There's nothing wrong with that. So if you make it react with something or water, okay, what is the bicarbonate doing in this instance? Well, it's acting like an acid, so it's giving away a hydrogen. And if something gives away a hydrogen, it behaves like an acid. So on the other side, we're going to have one less hydrogen than that which we started. So this is the hydrogen that's being donated to the water or to something. Okay? And then we'll form the other H3O+. But what I don't want you to do is write this equation right here. The question only wants this for an answer. Okay? But if you need to write out the balanced equation to get this, that's fine. But be sure to box in what the question is asking. Okay? All right, let's look at part B. And again, if you see a question that you haven't answered, or I've given you somewhat of an explanation for a previous one, try to answer it before you listen to this. So go ahead and pause the video. All right, part B wants to know, what is the conjugate acid for the bicarbonate ion? Now look at that. It's the same stinking thing, bicarbonate ion. But what's the question asking? It wants to know, what is the conjugate acid for this substance? Now again, I told you it was amphoteric, and this is a legitimate question. So if it wants to know what is the conjugate acid for this thing, you should say, what is the conjugate acid for this base? So treat this, in this case, as a base. Up here it was acting like an acid. And you know what? It's fine. So, and again, if you're getting all upset about the conjugate on here, simplify it even more. What is the acid for this base? What do bases do? Well, if we look at it, and if you want to show water, again, it's getting a hydrogen from something. So bases accept the hydrogen. So on the other side of the equation, we'll have one more hydrogen. And that's carbonic acid. So notice that the charge goes from -1 to no charge. And then the water turns into a hydroxide. So this thing acts like a base because it's acting like a base. So bases accept hydrogen. Acids donate hydrogen. Okay? Let's take a look at the next one, part C. Question is, what is the acid for this bicarbonate ion? I'm not trying to be mean here. I'm not trying to play tricks on you, but I just want you to see that this is an amphoteric substance. So the question is, what is the acid for this base? Pretty much the same question here, isn't it? B and C are the same. So hopefully you're going to say, based on the example that I gave up here, H2CO3. Because if this is a base, that means that they're accepting a hydrogen from something, from some acid, which we may or may not know. Actually, we don't care. We're just getting a hydrogen from something. And so it wants to know, what is the acid? Well, so on the other side of the equation, this is acting like a conjugate base, which is over here. So this equation is actually flip-flop. But again, the whole premise is, when you read this question, what is the acid for this base? Up here, what is the conjugate acid for this base? What is the conjugate base for this acid? Now, I may not be fully saying, what is the acid for this conjugate base? Okay, that's fine. But do realize all conjugate means is that it's on the product side. And what this question is asking for is just that. So you don't have to put it on the product side or the reactant side. Unless I've given you a balanced equation and I ask you to identify the conjugate acid or conjugate base. Then it matters which side it's on. All right, try D on your own. Okay, so you've had a chance to try D. So it wants to know, what is this? What is the base for this conjugate acid? So if this is acting like a conjugate acid over here, if you need to draw it, that's fine. That means it's giving away a hydrogen to something. We don't care what it's giving away. Okay, so on the other side, boom, there it is. Okay, so CO3 with the -2. So what is the base for this acid? Well, acids give away hydrogen. I hope those 4 examples have helped you to understand what this question's asking and not necessarily made it a little more confusing. All right, number 2. Wants you to write the dissociation reaction for each of the following acids and water and identify the conjugate acid-base pair. So, okay, and I saw a lot of weird things on the review today. One thing I want you to do, make sure you're reading the question. Okay, so it says for the following acids, and they're actually in water. So these are all acids because number 1, they start with hydrogen, and number 2, I told you they were acids. So how do acids behave? Well, they donate hydrogen and assume that everything is taking place in water. So if you want to include water, that's fine. I'll include it on this first one, but I'm not a big fan of including water on acids, but it's your call. If you want to do that, that's fine. So if you do that, remember, acids donate hydrogen. Okay, so we lose a hydrogen. We take it from the front. We never take it from the middle. So on this side, you'll have C2H2ClO2. And don't forget the charge. Since it's no charge over here, okay, and it gives away +1, it goes to more negative. And then since you want the water, then make sure that you include the hydrogen attaching itself to the water. Okay, so that's that. And then HCN, since I know it's an acid, I'm just going to go ahead and break it down accordingly. So I know it's in water. If you want to write water above that, that's fine. But do recognize that hydrogen ions and hydronium are the same thing. And then the CN with the -1 charge. Don't forget about the charges, guys. And then I had you change C to HNO2. So since it's still an acid, then we can go ahead and show it like that. And then the NO2 with the -1. Okay. All right. And then 3 wants us to write the equilibrium expression for each of those from question 2. So I'll go ahead and include all the components here. So we have C2H2ClO2. So we have C2H2ClO2 with a -1. And we have hydronium. That's a 3. And that's all over C2H2ClO2 with no charge. Be sure to include your charges. Okay. And then B was the cyanic acid. So I'll do it over here. So we have CN, -1, and hydrogen ions. And again, if you want to write your hydrogen ions first, nothing wrong with that. Also, notice no water. I did not place water in here because you don't put water in the expression. Pure liquids and pure solids never go in there. All right, and then HCN. And then C was HNO2. So NO2 and the hydrogen. Okay. So those are the expressions. Make sure you know the difference between expression and equation. And I sometimes assume that you guys understand what I'm saying when I say write the expression out. Always write the expression out for any problem that you're doing. Okay, especially if it's equilibrium type things. So the expression is products over reactants. The equation is what we did right here. So these are the equations, or the dissociation reaction. Okay. All right, number 4 says calculate the equilibrium constant K at a certain temperature for the reaction. And you'll notice that this is not an acid and base reaction, so I'm kind of tapping into your first semester or the last topic's information. I want to make sure that you still understand that, hey, I want you to be able to make ice charts and understand that there are some cases where you can't use the 5% rule. So let's go ahead and build an ice chart. So we have 2 ammonias. And again, this has nothing to do with acids and bases. This is just making sure you know how to write your expressions correctly and write your equations. So we ice it. Okay, so and really pay attention. If you need to start boxing in information like equilibrium concentration for hydrogen, is that not a bad idea. Initial concentration for ammonia is that. Sometimes we read the question, but we allow the words to intermingle or mean more than one thing. And if you understand what the equilibrium concentration is, it doesn't appear here, it appears at equilibrium. So I'm not given any information about hydrogen and nitrogen initially. We have nothing initial about hydrogen and nitrogen. The only thing that we have initial for is the ammonia, which is 3.22. Okay? The only information that's given for the hydrogen is at equilibrium. All right, so based on our coefficients, okay, this is going to be reduced by 2x, this will be increased by 3x, and this will be increased by 3x. Because again, we're going to shift to the right since we're not at equilibrium. Okay? All right, Then we're going to have 3.22 minus 2x, and then 3x actually has a value. It's our 0.85. So we don't need to write 0.85 plus 3x because that is 3x. And then x, we're going to figure out what that is here in a moment. So since we know a concentration at equilibrium and we know an initial concentration, don't even think about using a 5% rule. Don't do it. Once you have this information, you have the choice of either determining what x is right now or writing the expression. Well, I'm going to go ahead and write the expression because I want to get that out of the way. Okay, so it's just K, not Ka, not Kb, because this is not an acid and base reaction. These are all gases. So we'll have products over reactants. So we have our hydrogen, and that's cubed, and our nitrogen, which is not, over our ammonia, which is squared. Okay, and we're actually going to solve for what K is, so we don't have a value for that. All right, we also know that 3x is equal to 0.85. So we need to find out what that is. So 0.85 divided by 3. So it's 0.283 is x. All right. Now, since we know that x is 0.283, there's our value. For that, we have that in the way. We have our hydrogen. And now what we need to do is figure out what our concentration for the ammonia is at equilibrium. So we'll take, for this, we'll go 3.22 minus 2 times x, which is 0.283. So we need to figure these values out before we plug them in to our expression. Okay. All right, so we've got 3.22 minus 2 times answer, and that gives me 2.65. Okay, so there's my concentration for the ammonia at equilibrium right here. Okay, so now we have our values. Okay, we have our expression, hydrogen, nitrogen, ammonia. So we'll have K is equal to 0.85 molarity cubed times 0.283, and then divided by, we just said it was 2.65, and again our expression has a square on it, so we're going to square that bottom value. Okay, and there's an M in there too. Alright, so looking at the molarities, we have 4 on top, 2 on the bottom, so we'll have molarity squared, and then whatever our values are. So we have, I'm going to square that on the bottom since I have it in my calculator, take the inverse of that, multiply it by 0.85 cubed times 0.283. So, looks like it's 0.0247. Okay. And a couple people were saying, wow, that's a really small number. That's okay. It's all right. So we don't have to worry about the size of these values. And again, since we're not using 5% rule, we're good to go. Okay. So there's your answer. That's your K. Okay. Now again, this had absolutely nothing to do with acids and bases. But again, I want you to get more practice for being able to determine what concentrations are at equilibrium and not using the 5% rule. Because sometimes these questions are going to be asked on the AP exam and you're not going to get to use the 5% rule. Never ever use the 5% rule if you know something at equilibrium. If you know the value of X, if you're given a pH, pOH, pH and pOHs are always at equilibrium. Always. Or at the end if you're looking at a strong acid or strong base. Alright, looking at number 5. Okay. Number 5 says, if the equilibrium constant at 444 degrees Celsius for this reaction is 1.39 times 10 to the negative 2, calculate the equilibrium expression for the reverse reaction. Again, I think I mentioned this back in the last topic. I didn't mention it in acids and bases, but the concept is very clear. We know that we have a value, a K value, or an equilibrium constant, for this reaction. If you're not sure what to do, always start with an expression. So hydrogen, iodine, HI. Okay, and that equals 1.39 times 10 to the negative 2. Okay, boom, we got the equation. We don't care what the concentrations are. We don't care. That's not what the question's asking. However, if this reaction is reversed, what that's saying is hydrogen and iodine are now reactants, where the 2HI is the product. So what that means is we're going to have a different K value. So our K now will look like this. Well, we'll have HI on top because we have the reverse reaction, and hydrogen and iodine are our reactants, and it wants to know what is that value. Okay, well, here's what I want you to recognize. In the forward direction, this is our expression. In the reverse direction, okay, which is up here, or going this way for this equation, we have the inverse of our expression. So really what we have is an inverse for the value of K. Because at a certain temperature, when these guys react with each other, it doesn't matter if it's going forward or backward. They will achieve that ratio depending on where they start. So the concentration for iodine here is the same for the concentration of iodine there. Concentration of HI here is the same as the concentration there. Concentration of hydrogen is the same in both of these cases. It just depends on where it starts, if it's a reactant or a product. So when we answer this question, we're going to take the inverse of our K value from the forward reaction. Okay, and then whatever that equals on your calculator. Okay, so don't leave it at that. Actually, give me a number. So 1 divided by 1.39 exponent negative 2. So I get like 71.94. Okay, so it's 71.9. Now, here's a great concept question. If I were to ask, okay, which of these two reactions do you believe is more favorable? Okay, the top one here or this one here? Well, when we talk about favorable, we want to talk about a high K value. Certain things don't like to react very well. However, certain other things do like to form reactions. So in this case here, the very first one, the HI doesn't want to break apart too much and form hydrogen and iodine. However, in this reaction up here, the hydrogen and iodine want to form the HI quite quickly. So that's what's happening. HI breaks down and forms hydrogen and iodine. It doesn't want to be that way, so it reverts quickly back to the HI. So at equilibrium, we have more HI than we do H2 and I2. Same thing up here, except here we've got more HI, okay, because it's on the product side. That gives our value for K a much higher value. Don't forget, the K value represents products over reactants. So our products want to form a lot of stuff. That's why we have a value that's greater than 1. That's a concept, and we need to make sure that we know it, whether we're looking at regular equilibrium, acid and base equilibrium, and later on when we talk about solubility products, which deals with salts. All right, let's look at the next example here. Want you to fill in the missing information, and this can be just calculator work, okay? So when we talk about pH and pOH, don't forget about what you have available, what you have on the equation sheet. And here's the information that we're going to use that's on the equation sheet. You have pH plus pOH equals 14. You have that. I'm so surprised at how many people don't know what to do when they're presented with a problem like this. Also, what you have on your equation sheet is you have Kw equals hydrogen plus hydroxide, which is equal to a constant, which is 1.0 times 10 to the negative 14. These are two things that are on your equation sheet in the equilibrium section that a lot of you refuse to look at. And if you know how to do it, you can answer these questions without any hesitation. And we have got to get used to using our equation sheet more often. Okay? So if you have these two equations at your disposal, you can answer each one of these. All right, so, and then this part right here, okay, there's actually 3 ways that you can answer this question, whether it's an acid, a base, or if it's neutral, okay? Well, first of all, if you look at pH, okay, if the pH is less than 7, it is acidic. If it is greater than 7, it is basic. If it is 7, it is neutral, okay? So that's one way. Another way could be based on what we talked about on the first day of acids and bases, when you worked with this equation. Whichever of these two concentrations is greater determines whether or not it's acidic or basic. So if H concentration, the hydrogen ion concentration, is greater than the hydroxide concentration, you have an acidic solution. If the hydroxide concentration is greater than the hydrogen concentration, you have a basic solution. And if these two are equal, then it's neutral. Okay? We talked about that. You had homework problems over that and example problems. So please don't forget those. And then the third thing, depending on if you're looking at pH and pOH, whichever of these two values has the lowest value determines whether it's acidic or basic. So if I'm looking at, say, this first one, well, let's go ahead and get the value for the pOH here. So 14 minus 11.93, so it's 2.07. All right, so I've got this value here, these two values, 11.93 and 2.07. Which of these two is smaller? Correct, the pOH. Therefore, this deals with bases. So this solution is basic. Okay, now, here's another way. Since my pH is greater than 7, it's basic. What you don't have are these here. Okay, so to get the value for the hydrogen ions, I know my pH, so how do I get my hydrogen? Correct, I take the anti-log, I take the anti-log of the negative pH. Okay. Now, that equation, unfortunately, is not on your equation sheet. So you have to memorize that one. But the negative log, in other words, if you have this concentration, take the negative log of your hydrogen concentration to get your hydrogen, or to get your pH. Okay? So I'm not going to work these out for you, but it is important to know whether or not a solution is acidic or basic based on its pH or pOH, or the hydrogen or hydroxide. So you can easily look at the answers online to see what these values are. And again, this is strictly calculator work. Be careful, but excuse me, do realize that these two equations are at your disposal. Also, negative log of the concentrations are available, as well as anti-log of the negative p value are available. All right. Number 7. Wow, did I get a lot of questions about number 7 today. You must know your 6 strong acids. You must know your strong bases. Period. If you don't know your strong acids or your strong bases, simple questions like this will defeat you. Okay? You have got to memorize your strong acids and strong bases. Period. Because if you're looking at HNO3 and you're wondering, how do I work this problem out? It becomes very easy if you realize that you're looking at a strong acid, or in some cases a strong base. Okay? Because if it's a strong acid, it dissociates 100%. Okay? And this question is asking for this. Right here's the question. It wants to know how many grams of HNO3 are in solution. That's it. You have done this since General Chem. Very basic stuff. You have a volume, and you're given a pOH. Okay? Now, what I don't want you to do is freak out and say, whoa, why do you give us a pOH when we have an acid? Because you need to realize that everything has a pH and a pOH value. Okay? So again, based on what I said in the table up here, if you know pH or pOH, you can find the other. 14 minus whatever you're. Okay? So don't get freaked out whenever you see an acid and it's got a pOH. Okay? This is just information. That's all it is. And sometimes the information is given in a certain way to try to confuse you, but if you understand, I have a strong acid and this gave me a pOH, not a problem. I just need to find the pH. If I know the pH, I know the concentration of the hydrogen ions. Knowing that this is a strong acid, it dissociates completely or 100%. So whatever the concentration of the hydrogens, that's the concentration of my strong acid. And if I know the concentration, aka molarity, and I have the volume and I have the molarity, I can easily find out how many moles I have. If I know how many moles I have, I can find out how many grams. Okay? That's the process you need to be doing. These problems are not math problems where it's one step and you're done. Most of these questions have multiple steps. This is like life. You're going to have multiple steps to solving a problem. You're not just going to go in, take a magic pill, and you're finished. All right, so here's what we got to do. We have to realize that we have a pOH value that's equal to 12.44. You need to find the pH. So take 14 minus your pOH, which in this case is 14 minus 12.44, and that will give you 1.56. Okay? Once you have the pH, it's very easy to find the hydrogen concentration by taking the antilog of the negative pH, and if you have the concentration, you have the molarity for that hydrogen, which is your strong acid. So antilog of 1.56. So 0.0. So I have 0.0275. I'm going to leave that number in my calculator. So that's molarity, which is moles per liter. Okay, make sure you know what concentration means. I got some weird looks when I said concentration earlier today as well. Okay, so now here's what we've got. We've got a strong acid that dissociates completely. So the hydrogen ion concentration is that, as well as the strong acid, HNO3. Recall that dissociating 100% means however many moles I have at the beginning is how many I have at the end. So if you know how many you have at the end per liter, that's how many you had at the beginning. It's a 1-to-1 dissociation, period. All right, so now we know we have 400 milliliters. If you know your volume and your molarity, always start with your volume. Convert the milliliters to liters. Multiply that times the molarity, which changed the units to moles over liters. Okay. Then, now we can get rid of moles by multiplying it times the molar mass. Now, let's see here. Hydrogen's 1.008 plus nitrogen's 14.01 plus hydrogen's 3 times 16. So the molar mass for this is 63.018. Look at that. We have the unit we're looking for. Moles cancel out, liters cancel out, milliliters cancel out. Multiply everything on top, divided by 1,000, you have your answer. And I erased that value, so I apologize for that. So mine's going to be off by a little bit. So 0.0... Actually, 6.93. 6.93 times 10 to the negative 3. Not very much. Let me scoot this over a little bit. My pen's acting up now. Okay, so not a whole lot. And that's a 6 there. I apologize for that. Okay. All right, so again, recognize that you have a strong acid or a strong base, and the question becomes very, very easy as long as you know your strong acids and strong bases. Strong bases, solubility rule. I know you guys are not liking that I'm giving you all these solubility rule questions. You know your solubilities. This class becomes very easy at some point. All right. So know your 6 strong acids. I'm not going to tell them to you. I want you to go and look at them on the second day if you don't remember them. All right, number 8. Calculate the pH of a 0.237 molar solution of benzoic acid, and you're given a Ka. So it's an acid for a couple reasons, because I gave you Ka value and I told you it was an acid. Use the 5% rule. I'm not going to work this one out. You can take a look at the answers for that one. Here is a good one. Number 9. It says calculate the Ka of a 0.0062 molar weak monoprotic acid with a pH of 3.44. Question says do not use 5% rule and do not use the quadratic equation. Now here's what caused a lot of you to freak out. Monoprotic. Now again, if you're not sure about a term, go back and look in your notes. I put monoprotic at the bottom of the sheet on the first day. Monoprotic. Mono meaning one, protic meaning proton. One proton. Remember that a hydrogen ion is a proton. It's a proton with no electrons, so that's what a hydrogen ion is, a proton, period. Okay. So when we have our proton or our monoprotic, you get to pick. You get to pick what that acid is, as long as it has one hydrogen. Now, don't pick a strong one because, again, you have a Ka value here. So earlier on, we had cyanic acid, HCN. Pick something that's easy. Or if you want to be elaborate, do what you want. Or you can do what's on your equation sheet, HA. The H represents hydrogen. The A represents some anion. Again, don't make it rocket science here. So here's our dissociation reaction. We want to make an ice chart. So it dissociates into hydrogen and our anion. Look how easy that is. We can make life so much easier here. All right, so we know our concentration of our weak monoprotic acid. Bam. 0.0062. Hydrogen and the anion, we don't know anything about it initially. Don't make this stuff up. Now, you're also given a pH. When does pH occur? At equilibrium. So, when you work this problem out, make your ice chart. Okay, so it's monoprotic, so that means that we're going to reduce by x. So 0.0062 minus x. Here we're going to increase by x, except here, we're not going to put x because we know what it is. So, for me to find the hydrogen concentration, how do I do that? That's right, I take the anti-log of my negative value, negative 3.44. And that gives me what x is. So let's take that anti-log, so second log, negative 3.44. So x is equal to 3.63 times 10 to the negative 4. Okay. So now that I know what x is, that's my hydrogen and my anion, that value right there. So I have two of those values. And since I know what my x is, I can include it in here. So when I write my expression, and you want to write it, so Ka in this case is hydrogen times the anion over HA. Beautiful. I have 3.63 times 10 to the negative 4. Square that. And then 0.0062 minus 3.63 times 10 to the negative 4. Yep, include it. So that'll give you your Ka. So let's see here. I got that number. And what's great about the answer button, you don't have to type these back in if you know how to use your answer button. So I'm going to go answer square divided by 0.00 and open the parentheses, of course. So divided by parentheses 0.0062 minus answer, close the parentheses, equals. And I get 2.2, we'll say 6, times 10 to the 5, negative 5. Okay? Oh boy. I hope this video has helped. And again, I think a lot of the issues that most of you or some of you are having is that you're reading the questions too quickly. You're too concerned that this type of question hasn't been asked in the last 3 days. I need you to get past that, especially if you're going to be successful on the AP exam. You have got to remember the tricks from the past. Okay? So, again, if you have any questions, don't hesitate. Shoot me an email.